So welcome everyone to this month's Spatial ML seminar. And today it's my pleasure to introduce Stefan Abi-Karam. So Stefan is a full-time PhD student at ECE Georgia Tech under the supervision of Professor Callie Howe, part of the SHARC lab. His PhD research is mainly focused on designing electronic design automation tools, so EDA, field programmable gate arrays, FPGAs, and all sorts of different use cases and acceleration techniques for machine learning and AI. Stefan also has like another role, so he is a full-time like research faculty at Georgia Tech as well while he is doing his PhD. And this is part of the Georgia Tech Research Institute. And his research there are mainly focused on hardware security and trust. So all the different topics related to hardware security, trust, and assurance that applies to both electronic design automation tools and also different stages of the design and deployment of semiconductor solutions. So Stefan is graduating soon. So if you're listening to this talk online or live, he will be looking for academic jobs very soon. So please reach out to him. I personally met Stefan first time at the FPL conference a few years back. And we had a lot of very, very interesting discussions, and he had a lot of interesting questions and interesting ideas for all the different papers presented. So if you're looking for a very good future faculty member, please reach out to Stefan. So Stefan, the floor is yours. Please go ahead.
Cool. Thank you, Andrew. Yes, hello, my name is Stefan. Today I'm talking mostly about HLSFactory. This is a work we presented at MLCAD 2024, and we also won Best Paper, which was nice. But this was a collaborative project across both Georgia Tech, ASU with Professor Aman Arora, and University of Texas Austin with Professor Lizzie John, and then also my own advisor. And so yeah, we'll get right into it. Let's see. So this is like the official logo for the project as opposed to just the icon. But this is a brief overview of what I'll mainly be discussing in the presentation today. So to get into it, at a high level synthesis research is very multifaceted, that has many branching subtopics, and they overlap a lot. So for example, if you think about at the application algorithm and high-level design side of things, this is more of like application. So think of people who use high-level synthesis for high-energy physics, for autonomous driving, image processing. This is when you're designing your accelerator, not necessarily like at the Verilog level or even HLS level, but you're still modeling things in PyTorch and Python and so on and so forth, right? So once you've come up with your application and potentially what you want to model with high-level synthesis or accelerate, then you get into the actual HLS tool itself, right? So research in this area about the actual HLS compiler is usually split up into many different subtopics. So you could be looking at like the front end, the lowering and the IR, you know, how the most HLS compilers will use like a Clang or LLVM in that front end step. Then you have scheduling and binding. So this is more of like the heart of how high-level synthesis tools work. And then you have, you know, HLS code generation. And this area of research is actually mostly focused on, like I said, the compilers themselves. So I highlight kind of like a brief overview of what, you know, most common HLS compilers you might run into. And then, you know, once you go downstream from that, once you have your HLS design, then that's all goes into traditional hardware design flows. So that has to do with implementation and then deployment and integration into the real world. I know there's HLS for FPGAs and there's HLS for ASIC. I'm an FPGA guy, so most of my examples and my use cases are going to be for HLS tools for FPGAs, mainly Vitis HLS. But we'll also talk about Intel HLS tool as well. So if you think about like if you were to pigeonhole yourself into like a specific area for a specific research project, you have kind of like high level architecture, then you have compilers, and then downstream you have VSLI, right? And some of these research areas kind of overlap, but they're mostly self-contained, right? And then once you start looking into common techniques like DSE, design space exploration, software hardware co-design, and then if you start building machine learning models to do like performance prediction across different stages, modeling of your accelerator performance, so on and so forth, this kind of research mostly spans all stages um, of high level synthesis research. But I think there's actually one kind of research here that I haven't shown yet that is actually more fundamental than all these topics. And that's benchmarking and design data, right? So design data and benchmarks are fundamental to all HLS research. You need data to, you need design data to be able to build different models, do design space exploration. You need benchmarks to look at compilers and optimize HLS compilers. And also you need all this information to do informed architecture design and also tune downstream VSLI tools. And the idea is that high quality, plentiful HLS data should be available to everybody with little effort, right? Since it's fundamental to the whole field, it should be a priority and easy to access and plentiful without any issues. So really quickly an aside, why might one focus on this data thing now? And what one reason is that a lot of people are looking at machine learning and deep learning for HLS. These examples are actually outdated a little bit, but to get an idea, these would be things like, trying to predict timing and resource usage given an HLS design, maybe at the source code level or at the IR level, and try to predict, downstream post-synthesis resource usage and timing information. You might also want to do something like power estimation. You can run like an HLS tool. It'll give you like a rough, generated HLS design, but then before running implementation, like full place and route, you can use that information to try to predict power. And then also once you kind of build these models for timing, resource usage, and power, you can then do stuff like design space exploration much quicker. HLS tools can take on the order of like minutes to hours, and then the implementation tools can take on the order of minutes to hours to days. And so once you build these proxy models, you can do this kind of fast DSC over these design spaces. Right. So specifically for ML for HLS research, it requires high quality, unique HLS designs. And so that means designs that are distinct from each other. So you might have one design where you might try to take the single design and vary the pragmas in the design, and you consider those to be different versions or different data points. What I'm talking about is that you have two distinct designs. So you have one kernel that's like a matrix multiply, some other kernel that's like an FIR filter, or some other stencil computation. Those are two distinct HLS designs, right? And then you want to sample those designs over a large space of HLS optimizations. So for a given design, we also still want to have many variations of that design by trying a lot of different compiler optimizations over that one design. So we need both of those in order to train ML models for HLS that are robust and successful. And so what kind of data comes out of an HLS tool with a given design? So you're going to start with your original design benchmark kernel code. So usually HLS languages are C++ or C based, and those are usually passed into the compiler. And so you have your kernel as source code, usually C or C++. And then sometimes you have some kind of design space that you know ahead of time as the designer. This is optional. So in this case, I might have a loop in my HLS design, and I might want to try to unroll the loop, and I know that I want to try different values for the unrolling factor, right? So I can collect, all those different range of values that I want to try for my design. Once you pass your design into the HLS compiler, the front end will usually lower your design from the high-level language into some kind of IR. In this case, Vitis HLS uses LLVM IR. Then you get the results from scheduling and binding from synthesis. And so this basically is what the HLS compiler determines it wants the schedule of the operations to be. And then binding allocates different nodes to different hardware resources in the device. And then once you have all this information, it then generates the appropriate HDL for that solution it synthesized. And then sometimes it also packages it as an IP block as well for whatever vendor downstream. And then additionally, HLS tools will provide text or XML-based kind of reports for latency and resource usage. And then if we just take the HLS design and then run it in our traditional implementation tools, we get all the data that we would normally expect. But mostly what I'll focus on is reported data after implementation. So after places route, that's things like timing, actual resource usage, power, things like that. So the idea here is that if you have the source code for your design benchmarks, you can generate all the other data. That's all something that can be automated away, right? So that's really good news for us. And then having different variations of your HLS design space optimization parameters lets you also generate many versions of a single design. And so these are kind of the two ingredients I was talking about earlier. So once you have this automation and once you have this design space, it's really easy to generate tons and tons and tons of HLS data. And so some people kind of have explored this idea in the past, looking at taking different benchmarks or collecting data from different parts of the design flow, but usually they miss a lot of gaps. So for example, one common issue is that a lot of these previous works don't collect like scheduling and binding data or collect like the generated like LLVM-IR. It's only just like design and report information. And that's not particularly useful, let's say, if you're trying to train a neural network, like a graph neural network, to take an input of the LLVM-IR, for example, right? You can't do that unless you have that data. And so the idea, and then also one other thing is that many previous works try to focus in on one specific vendor. That can also be a limitation. So basically, we try to address all these points and cover a lot of these different features that other works are not covering when it comes to HLS dataset collection and generation. So at a high level, the main motivation, an issue that we see is that like there's not a lack of another data set, but really there's a lack of easy to use infrastructure or tooling or software to like build these data sets, generate all of this data, collect it, organize it in order for someone to just take it and then run experiments with. And so users should be able to like submit HLS designs into a centralized, community location. It should be easily able to merge in existing data that they've already generated with each other. And they should also be easily able to parameterize designs to generate many variations of them. And then, other things that we would like to see and that are limitations right now for users is that data quantity. So, right now there's not a lot of HLS data that's being generated or that's even out there, and quality, right? So there's not a lot of data from different vendors or unique HLS designs, right? And so to summarize here, HLSFactory is not necessarily its own data set, but it is a framework for building high quality HLS data sets, right? And so we have a lot of different features in order to do this. And then we have a lot of built-in designs primarily to as a starting point for users. And I'll get into all these different points as well. So getting actually into HLSFactory, we kind of organize HLSFactory into kind of 3 stages for the user to think about. So stage 1 is mostly about like inputting design sources and doing this thing we call design space expansion. Stage 2 is just about like the actual like once you have all these designs, how do we automate, running it through all the tools and collecting the data. And then stage 3 is just aggregating all of that data and then packaging it for researchers. So at the end, the user can just get one nicely, cleanly packaged data set that they can then use for their own downstream research. And then this is the expanded figure from the paper, but I won't go into too much detail right now. So the first stage, as I mentioned, is this design sources and design space expansion. And so the idea here is that we wanted a way for users to be able to parameterize HLS designs to generate many versions of them, right? So we have this concept of a abstract design and then a concrete design. A concrete design is one that you can just take and just plug it into a HLS vendor tool and it will build. But an abstract design needs to be parameterized. It has, missing things, or the pragmas need to be filled in, and so on and so forth. So the idea here is that, like, let's say you have, in the previous example I mentioned, you have a kernel with a for loop and an unroll pragma, and it has a factor, but we haven't filled in the actual factor value. We have a set of unrolling factors in which we like to try, and then through some abstract thing I have not mentioned yet, we can generate different versions of this design by filling in this factor. What I'm about to describe with this abstract to concrete design is very simple. It's not rocket science or anything like that, but it is what allows us to generate much more data and much more varied data. So yeah. And then just highlighting the different factors that are filled in place of the original factor placeholder. And so what is this like design parameterization? There's a lot of ways to do this. So I'm going to talk about what we come up in the paper called OptDSL. But keep in mind that there are many different ways to parameterize, source code. You can literally do string templating or run it through a C++ preprocessor. And HLSFactory lets you write your own front ends to do this. But I'm going to focus in on the one that we talk about in the paper. So, let's say, same example, you have a loop, you might want to unroll it, but you also have other factors, maybe you have pipelining pragmas that you have, you want to say on, off, don't pipeline or pipeline this part. And then you also might have array partitioning pragmas. So the idea here is that we want to generate all variations of a design given its design space, right? So this is not design space exploration. There is no optimization or guided search. We're not trying to make something as fast as possible or find, the best design. We're just simply want to generate and enumerate the design space, right? To generate different varied data points. So in this example on the bottom left, there's 15 possible designs that we could, parameterize here. And, like I mentioned before, the way we actually do this parameterization, I get for Vitis HLS, is that you're allowed to have a separate, you're allowed to put pragmas in TICL files that are read by the tool. And so we basically, for a given design, we just copy the source code and then we create a new opt TICL file, and then we insert, the different variations for those pragmas. Like I said, it's very straightforward. There's nothing, complex about this. And then each of these become individual concrete designs as well. So that's cool. That's pretty simple to automate, it seems. But the issue is that how do I programmatically specify what the design space is for a given design, right? I have it in the slides, I show you a table that I made in PowerPoint, but how is the user supposed to describe that so that the tool can automatically then go on it and parameterize that? And can we make that vendor agnostic, right? And so the idea is that we have this custom design space DSL called OptDSL. It has the syntax for defining all these different things. I'm not going to go into too much detail, but basically we support loop unrolling, pipelining, and array partitioning, and it's agnostic to Xilinx and Intel HLS flows. So basically this file will exist alongside the design source code. HLSFactory will find it, and then it's able to parameterize it's able to load this in, build a model of the design space, and then sample from that. I will note that currently we are working on a way better syntax for OptDSL, actually mostly motivated by LLMs. So this syntax is horrendous for LLMs to understand, and we would like LLMs to be able to um, reason about this opDSL, write opDSL kind of stuff. And so we have significantly improved what this looks like, I will say. But this is what we have in the original work. And as an illustrative example, you take your design source code, you take this opDSL spec, probably as a text file, and then you can generate, different, variations of designs for both Intel and for Xilinx. So it'll automatically be able to do both, which is very handy. Switching gears a little bit to the actual design sources. So in HLSFactory, we actually include built-in design sources for common HLS benchmarks. And so what I'm presenting now in total has 53 benchmarks. These are from things like CHStone, MaxSuite, Polybench, and Rosetta, which are the most common HLS benchmarks in the community. And I will talk about adding more designs later because we have done significant work on that as well. And then to also note, we actually created the opDSL like design space description for each design, right? So, and this is all built into the Python package itself. When the user wants to run and build designs, they don't have to like download anything. If they have HLSFactory installed, these designs are in there. The opDSL descriptions are in there. They can hit run. So the second stage of the entire HLSFactory flow is around this build core. Essentially, it's we're basically building a build system, and we try not to make it super complicated. I'm not going to get super into the details about like this automation because it is also mostly engineering work. One important thing is that we add this fine-grained parallelism, which lets us build tons and tons and tons of Vitis HLS designs in a very parallel fashion. But yeah, it's pretty self-explanatory. The only thing I will go into detail here is that there's a specific way the build system works, and the idea is that as long as you have certain entry points in your design, and that the build system is able to find those specific entry points, then it's able to build the design. So essentially, what I'm trying to say here is that it's very easy to add designs. You just copy over, let's say you have an HLS project, you copy that over, and then you simply need to make sure that you have a specific tickle file which acts as the entry point, and then HLSFactory is able to find that and then just automatically run your thing. You don't have to change the structure of your project. You don't have to change, how you organize your source files, so on and so forth. Additionally, all of this is wrapped in a Python API for the user. We have these abstract flows and front ends and tool flows and stuff like that. And we implement different ones for Vitis and Intel. And users are able to add their own flows for whatever tool they want to run. So for example, if they want to run they built some custom HLS simulator and they want to run that, you can add a flow as well to do those kind of things. So here's like a minimal working example of HLSFactory, where you basically, let's say I load in Polybench, MaxSuite, and CHStone designs. I run this opDSL front end to generate, for each design, generate 10 samples of that design. And then I run it through HLS synthesis, HLS synthesis. It will gather the report data. It'll run it through Vivado implementation, and then collect all that report data as well. This is literally the only thing that you need to collect all of that data. And then finally, we have like a last step for dataset aggregation. Essentially, what it does is that once when you build your Vitis HLS project and your Vivado project, there's a lot of different things everywhere, such as reports and for example LLVMI or bitcode, all this kind of stuff. And so we have these aggregators that simply go into each design, pull out all of the relevant data files, and then for any tabular data, it'll aggregate them together into a CSV, and then for any artifact style data like files, it'll organize them into proper directories, and then essentially it tar GZs everything into one file and then hands it off to you. So you can just take that and then, like I said, use it for downstream research. One interesting thing is that, like, let's say there's published results, from some other source or paper or something like that. You can also pull in that data as well during the data aggregation step. Now, one interesting thing about this work is that we did a lot of case studies to demonstrate the utility of the framework and also the utility of the data itself, right? And so I'm going to talk about 7 different case studies. And I think the more interesting point here is that each case study is designed and evaluated in less than 4 PhD student hours. So every case study took, end to end to do the case study is just 4 hours. The first, example or case study that I have is about ML prediction for quality of results. And so this is what you might consider like a very simple or baseline style ML for HLS task, right? So we have some kind of design which we run through Vitis HLS, and we get some kind of report about the latency resource usage, and then we run Vivado, and then we on the generated HLS design, and then we get timing and also resource usage and power, right? And so the HLS reported metrics can be significantly different compared to the post-implementation metrics. Actually, as a word of warning, the HLS reported metrics are also usually like very, very incorrect in their own right a lot of the time. But they are also significantly different from the implementation metrics in a lot of cases. Especially, I guess this is caveat for just Vitis HLS and Vivado. I'm not sure about other tools at the moment. And one thing that we also want to note is that running Vivado to get the real, resource usage, max frequency, power, those kind of metrics, it takes much longer. It's much slower than running Vitis HLS. Running Vitis HLS can take, a couple minutes, and then Vivado can take like 30 minutes or an hour. So the idea is that can we predict the implementation metrics only given the HLS reported metrics, right? So the idea here is that we have some kind of simple ML model, and we take the Vitis HLS generated metrics. These are estimated, and then we also take in different, aggregated counts of different LLVMIR instructions as input features. We wouldn't be able to do this using previous data set efforts. Since HLSFactory collects this data, it's readily available to use. And so we take both those things and we just use a simple decision tree model, and we try to predict the Vivado reported metrics. And in this case, there's even metrics like Slack that you're not able to actually predict or estimate at the HLS level as well. But in summary, that we can show that we can close the gap between like the HLS reported metrics and then the Vivado implemented metrics with this kind of model. Like I said, we can predict timing slack, which is something you can't estimate at the Vitis HLS level. And mostly we show that the more data that we're able to collect, from doing this like design space expansion, the better performance we get as well. This is what I would consider to be more like a baseline ML task for HLS. Some other things that we wanted to visualize is that what is the distribution of the generated design data look like? And so we can see here that let's say we take the base designs, from Polybench, MaxSuite, and CHStone, and we, build all of those, and we collect their metrics, and we plot a histogram of their latency and resource usage. That is the green histogram. So you can see here that the green histogram, for at least for latency, is limited to a specific range of cycles we see in our built designs. But as we do this design space expansion off of those base designs to generate different variations of those designs, we're actually able to cover a wider range of design of latency values that we see in designs. The same thing is true of resource usage, and especially for like DSPs, for example, where the base designs only cover designs that have a low number of DSPs. But as we do this design space expansion, we actually see more designs that are that have much more DSPs than just the base designs, right? And this is important for having robust data for ML training, that where the ML model is able to generalize across bigger ranges of designs. One other thing that we can do is that we can visualize what does this design space look like. And so the way this visualization works is that every solid point that's like highlighted and is a little thicker, those points are the base designs, or the base kernels, without any pragmas or anything like that. And all of those tiny points on the figure are designs that are from the design space expansion. Those are variations of those base points. And all the yellow designs represent Max Suite designs. All the red designs are CH-Zone designs. And all the blue designs are Polybench designs. And what we did is we built those designs, we took the generated metrics, and then we did some kind of dimensionality reduction to visualize it in 2 dimensions. And what's interesting is that we see that different design sources, so like Max Suite, CH-Zone, Polybench, cover different parts of the design space, right? So design space expansion allows us to also expand the range of these kind of like polygons that show the design spaces of different benchmark sources as well, right? And so this is the same example, but broken down by individual kernel, right? So this kind of shows the effect of design space expansion much more. So for example, in the top, in the middle, there's this orange kernel, and you can see here that the base point versus like the polygon created by all the design space expanded points allows it to cover more design space. This case study mostly is just highlighting some engineering effort that we did to have this fine-grained parallelism. So we have a lot of features like supporting timeouts, supporting building designs from different sources and data sets using multiprocessing. There's nothing really here that's necessarily novel per se, but there was a lot of engineering effort that went in order to make sure that we can build at a much larger scale on larger clusters or larger computers. One other thing that I mentioned earlier is that we're able to target different vendors. So this is the same histograms that I kind of showed before, except this is just targeting Intel HLS instead of Vitis HLS. I can make the same figure and collect the same data without any issue. So one other effort that we were that we worked on during the initial version of HLSFactory is that we wanted to add more designs, right? So we have these common HLS benchmarks that are in the community, and so we wanted to further that, and we added more designs from Xilinx's examples. We added designs from the Parallel Programming for FPGAs book, and then we added designs from accelerators that we built in our own Shark lab as well. We can also import data, like I said, during the aggregation stage from other published works. So for example, we can take the data from this work called HLS Sin from Jason Kong's group, and we can plot that against our own data since it's all aggregated together as well. And then the last case study I'll talk about is actually my favorite case study. So this is regression benchmarking for different versions of the tool. So a lot of times, something might work in one version of Vitis HLS and then break or become much worse in a different version. So for the same design, can we observe changes between different versions of the tool, like in runtime, latency, resource usage, and are these changes statistically significant, right? So what we do is we take one design, take the same design and run it through 2 different versions of the tool. We get some estimated reports, and we compare them, right? And so we can do this experiment really easily with HLSFactory, and we can plot like the distributions of runtime or reported latency for the same design as histograms for one version versus another version. We can do non-parametric statistical tests to see if there is a significant difference for any of these metrics that we're looking at, and so on and so forth, right? So this is not, ML related, but it's still very useful, and I think especially useful when it comes to the statistical testing, when looking at EDA tools, improvements, new research in this kind of direction. And so one other thing that we wanted to emphasize is that all of this work is open source. We put a lot of effort into the documentation, making it easy to install, so on and so forth. So if you're interested, please go check that out. We have a lot of current ongoing work when it comes to HLSFactory. So more HLS designs, more vendor tools, different kind of flows, and more data extraction. And so we hope that as we keep working on this, other people in the community will come join us and also contribute to this as well. Some two quick works that I wanted to highlight that are like currently ongoing is that we are collecting significantly more HLS designs. So we're working with Professor Jason's group to collect all of their years of accelerator and HLS designs, add them to HLSFactory. We have constantly new HLS designs from my own Shark lab. And then one other project that I'm interested in exploring is that can we index, all FPGA and hardware-related conference papers from the past 10 years and try to go and hunt down all of those HLS designs that exist there. One other work that came out of this work was that can we, look at LLM for HLS design? Everyone wants to use LLM to write Verilog, but no one cares about HLS. So I was able to take a lot of the designs that were cleanly organized in HLSFactory, turn them into a benchmark for LM evaluation. And this, you can go read this on arXiv, but this will be presented in more detail at ICLAD in June. But the short answer, if you're very curious, if LMs are good at HLS design, the answer is not yet or no. It's not very surprising, but there still needs to be a lot of work done in order to do this benchmarking, more advanced tasks, more complex, LLM flows to be able to do that. So, one last thing I want to emphasize is that this work is not just like me by myself. There are a lot of people that contributed to HLSFactory, especially from our own group and other universities. And so I just wanted to highlight that as well. Yeah, and that's all I have to present for today. I think this is a good time to take questions.